All right, good. So now in the next 10 minutes, let me tell you a little bit about electronic instabilities, and in particular, which kind of electronic instabilities we can have in two-dimensional materials. And of course, this is something that we will address in detail, both in superconductivity and magnetism sessions. But this is a good motivation. So for example, if you just take the electronic structure of graphene, which is the one that you see on the left, if you now start adding large electronic interactions, and you can just take, for example, Hubbard interactions or first neighbor repulsive interactions or any other interaction that you want, what you actually see is that a gap opens up at charge neutrality. And this is something that it is fairly common of any electronic system when you introduce electronic interactions. So you can think that electronic interactions, what they want to do is they want to lower the energy of your system at any cost. And by any cost, it means by open a gap in any way that it's allowed for that interaction. So if you can come up with a term in your Hamiltonian that opens a gap and can come from the mean field of that interaction, then that type of term is likely to appear when you do the mean field calculation. And in other words, if in graphene you can open a gap by creating a charge density wave, then it is likely that electronic interactions may be able to create that charge density wave intrinsically. If you come up with a term that can open a gap leading to antiferromagnetism, then there may be some interaction in graphene that gives rise to antiferromagnetism and so forth. And the same with superconductivity, the same with non-collinear magnetic order, and the same with other orders that we are going to address. Of course, in the case of graphene, we do know that this doesn't happen in reality, right? So graphene doesn't have a gap by itself, at least in the two-dimensional limit. So we know that at least in graphene, we are in the limit in which interactions are not strong enough for opening a gap. But for example, if we start patterning graphene, for example, if we start going to one-dimensional systems, or if we start adding defects, then we may be in the situation in which electronic interactions can overcome the kinetic energy, and we can see it on the right side. So let us explore now a few cases of this. So maybe the simplest case to think about is this one. It's just, again, graphene, a nanoribbon, but a slightly different nanoribbon than the one that I showed you before. So before we had something that was called an armature edge. Now we have something that is called a zigzag edge. So it's called zigzag because, of course, you have a zigzag on top. And the very nice, interesting feature of this kind of zigzag nanoribbon, and again, this is still just graphene, is that you have a band that is nearly flat here. And of course, when you only consider first neighbor hopping completely flat. And every time that you have a flat band in the electronic dispersion, then you have a divergent density of states. And let me emphasize that this divergent density of states, it is not there when you consider infinite graphene, right? In infinite graphene, you have a V-shaped density of states with a 0 density of states at charge neutrality. But if you make a nanoribbon, suddenly you get a divergent density of states. And if you make the nanoribbon wider, you get the very same thing. So you still have flat bands, you still have your divergent density of states. So this divergent density of states is going to appear in every single zigzag nanoribbon that you consider. And of course, the states that are giving rise to this divergence live, let's say, very close to the boundary, because of course, here in the middle, you will have almost bulk behavior. But what is important is that just with a carbon structure like this one, you can get a divergent density of states at charge neutrality. You don't have to dope the system at all. And of course, you can look at this systematically for any width, and you always get flat bands, no matter how wide your ribbon is. And of course, as you go to wider and wider ribbons, you start recovering your Dirac dispersion for the bulk states. And in all the cases, you have your divergent density of states at 0 energy, no matter the width. And of course, when you go to very long widths, you also recover the V shape here from the bulk states. All right, good. So what is important, and of course, if you have any questions, please stop me at any point. Oh, Yes, that's a very good question. So what are the applications of materials with a flat band gap? So essentially, every time that you have a flat band, you have a divergent density of states. And every time that you have a divergent density of states, you can have any sorts of symmetry broken states driven by your Coulomb interactions or any other many-body interaction. So flat bands and divergent density of states are the perfect starting ground for having any type of magnetism that you may imagine, any type of superconductivity that you may imagine, any type of correlated topological state like a fractional Chern insulator, for example. In short, any type of state that is driven by interactions has a wonderful starting point in a flat band. So if you want to look for symmetry breaking, having a divergent density of states and a flat band is a great starting point.
So we are increasing the width of the zigzag and
yeah, so we are increasing the width of the ribbon, so the y direction here. So this is infinite in the x direction, and we are increasing the width. And what I was mentioning is that one gets flat bands a divergent density of states, no matter the width of your zigzag ribbon. Yeah, so it's the width is the difference between the top and the bottom. So let's say 10 nanometers or 15 nanometers or 20 nanometers and so forth. So you always consider that the ribbon is infinite in the x direction. That is why you have a band structure with the momentum in the x direction, but then you can change how many atoms you have in the y direction.
That keeps being flat when you increase this picture. What is the reason for why we go back to the graphene? What is the reason?
Oh, that's a very good question. So, for example, let's look at this ribbon here. So if one looks at where these flat band states here are located, they are located just at the top of this edge and at the bottom of this edge. And then if you look at the density of the states right here in the middle, what you would get is actually just a V shape. So this electronic structure, of course, it needs to account at the same time for all the atoms in your unit cell, right? So both the atoms that are here in the middle and both the atoms that you see in the top and in the bottom. But if you look at how the wave functions are, what you see is that the wave functions of this flat band, they live up here, whereas the wave functions of all the wave functions that are here in the bulk have zero weight in this flat band. So that is why you see the flat band all the time. Yes, it's a topological property. So this flat band can be understood as coming from the Berry phase of graphene. So in this part of your electronic structure, you have zero Berry phase. Here you have pi Berry phase, and these flat bands are essentially come from that. And that is also the reason why they appear in a zigzag edge, but they don't appear on an armature edge. Just because on an armature edge, if you look at the projection of your reciprocal space, then you don't have these two regions with zero and pi Berry phase, because your valleys get folded to the very same point. All right, great, wonderful. So now let us continue with that. So following up on what you mentioned, if one computes the local density of states at zero energy, which is a different way of looking at the wave functions at zero energy, what you actually see is that all the wave functions at zero energy, they live here in the bottom edge and in the top edge. And if you start making the room wider and wider, you will see that all the time the wave functions at zero energy, they live in the two edges. And that is the reason why you always see them, because any ribbon has an edge, and any ribbon will have these edge states. And of course, that's also the reason why in pristine graphene, we don't see this divergent density of states at zero energy, because pristine graphene lives here in the middle. All right, good. So now what we can do is we can just introduce interactions in this model, right? And in particular, we can introduce local Hubbard interactions, which are the interactions that we were essentially considering when describing the mean field approach. And if we introduce Hubbard interactions with positive U that essentially realize repulsive interactions, we expect magnetism in particular. And the interesting point is that even if you consider the simplest type of magnetism that you can have in this system, which is, let's say, all the spins pointing up here, then you may have two choices between one edge and the other, right? So you may choose that all the spins point up here and all the spins point up in the top, or you can consider that the lower edge has all spin up and the upper edge has all spin down. So each edge is ferromagnetic with itself. So all the spins point in the same direction within the same edge, but in between edges, you can have two different configurations. And if you do a mean field calculation, you actually find those two solutions at the same time. You can find a solution in which the two edges have magnetization in the same direction, which is what we call the ferromagnetic alignment. And you can also find the configuration in which the different edges have magnetization in opposite directions. That is the antiferromagnetic configuration. So, of course, now the question is, well, quantum systems have one ground state, right? Or, I mean, if they have several, they may be equivalent, right? But here we have clearly found two ground states that are different, right? So there's one, well, ground state, quote unquote, that it's metallic, right? And that it's ferromagnetic. And we have one ground state that is semiconducting and that it's antiferromagnetic. So they are clearly inequivalent. A metal is different from a semiconductor. And therefore, only one of them can be the true ground state. So this is something that actually happens very, very often when you consider interactions at the mean field level in an electronic system. You may find many different, let's say, self-consistent solutions that are self-consistent, namely that they verify the mean field equations, but that they can have different properties. And this is one case. So one state that is ferromagnetic, one that is antiferromagnetic. We can also find cases in which one self-consistent solution gives rise to superconductivity, the other self-consistent solution gives rise to a charge density wave that it's an insulator, so clearly different states. You can also find many different systems in which you can stabilize many different magnetic solutions at the same time, and so forth. So now the question is, how do we know which one is our ground state, right? How do we know which of our self-consistent solutions give rise to the lowest energy state, and of course the one that we expect in the experiment?
Before you go on, just check. Do you know which one of these is metallic and which one is here? I guess it's not clear to everyone. It might be important also.
Yes. Yeah, that's a very good point. So, so the one here on the left is metallic, as you well said, and the simple way of knowing is, let's say your chemical potential is at 0. So if your chemical potential crosses a band, then you have a metal. If your chemical potential does not cross a band, then you have a semiconductor or an insulator, and yeah, depending on how big the gap is. All right, great. So yeah, that was a very good point. All right, good. So now the question is, how do we distinguish between these two different solutions? How do we know which one is the true ground state? And at the mean field level, you can do something relatively simple, which is just compare the energies. You may have different solutions that are self-consistent, but of course the ground state is going to be whichever solution has the lowest energy that you can build with your mean field approach. So now my question for you at this stage is, which one of these two configurations has less energy? And I know that it's not a simple question, but just share any thoughts that you have. So how would you compute the energy of a system just coming from the electronic structure? Yeah, All right, but imagine that you don't have the wave function. Imagine that everything that you have is this picture. Yes, just from the picture. The one on the right.
Yeah.
Why?
You have just said that when there's suburban from each other.
Yes, that's absolutely perfect. So that's exactly the trick. So since this system is insulating, your energy is going to be lower. And one of the arguments is what she mentioned. The other, let's say, more kind of mathematical argument is saying that, well, the total energy of your system is going to be kind of proportional to the sum of all your eigenvalues. And all the eigenvalues here and here are pretty much the same. And the only ones that are different are those close to the Fermi energy. And if you have a gap, clearly your eigenvalues are going to be more negative, and therefore your energy is going to be, let's say, lower. So why do you say that there's lower interactions? Yeah. Yeah. Of considering it. So yeah, that's of course something that we can think about. Then in general, if you want a rule that will work in most of the cases, just think about how big is your gap. The bigger your gap, usually the better. Let me emphasize that this is not the whole story. There's one more term that matters for the total energy, that is a double counting term that one cannot see from these pictures. And that term can be, of course, important for certain cases. But for most of the symmetry broken states that we are going to consider in the exercise sessions, just by looking at which one has the biggest gap, can already give you a very good hint of which one has the lowest energy. All right, good. And of course, this type of electronic interactions is something that doesn't have to happen on flat bands. It can also happen in dispersive bands. And now here, let me show you a very specific example, which is with the electronic structure of vanadium diselenide or vanadium disulfide, which can be described by a single orbital model in the triangular lattice. So vanadium disulfide and diselenide, they also have a charge density wave that it is not included here. But if they didn't have a charge density wave, their band structure would be this one. And according to the quantum chemistry calculations, they actually have a ferromagnetic instability that gives rise to this type of electronic structure. So in short, the electronic structure of vanadium diselenide or vanadium disulfide can be described also by a single orbital model in the triangular lattice, and the ferromagnetism comes directly from a, let's say, local Hubbard interaction, for example. So in other words, one can also have electronic instabilities in systems that do not have flat bands, provided the interaction is strong enough in comparison with the bandwidth. And this, of course, just a specific example. And of course, in this type of models in which bands are not flat, depending on how strong your Coulomb interaction is or your on-site interaction is, then you may have a more or less correlated state. So in particular, if you have no interactions, you just have a metal. Then if you have, let's say, modest interactions, you have a system that has ferromagnetism because it has a spin splitting, but it's still a metal. And then if your interactions are very, very large, then you have essentially a mod insulator. Yes, in this model, yes, because one doesn't have spin orbit coupling. So if you don't have spin orbit coupling, in principle, all the directions for the magnetization have the same energy. Once you have spin orbit coupling, then there can be a preferred direction for the magnetization. That is, of course, something extremely important for two-dimensional materials, and in particular for out-of-plane ferromagnets. All right, good. So then let me quickly tell you about proximity effects between two-dimensional materials. which is essentially what happens when you put one two-dimensional material together with another one. So let us just imagine that we have a material that is a ferromagnet. So you can think about the electronic structure that we had before, and we can see how this ferromagnet can affect a system that it's not ferromagnetic. So for example, a semiconductor. And the typical semiconductor that we can think about is, for example, MOS2, tungsten diselenide, tungsten disulfide, and so forth. So all these semiconductors, all the dichalcogenides, have an electronic structure that is relatively similar. So they have pockets around K and K prime. They have a full gap. And they also have intrinsic spin orbit coupling that it's known as Ising spin orbit coupling. And I mean, of course, this is not the electronic structure that one gets from quantum chemistry, but this is just the minimal electronic structure that one can write down with an effective model that captures, let's say, all these different phenomena at the same time. So something very interesting about these dichalcogenides is that at low energies, they are effectively described as a Dirac equation that has a mass that it's spin and valley dependent. So dichalcogenides are like a massive version of Dirac electrons, whereas graphene is a massless version of Dirac electrons. And in particular, this spin splitting that they have here is maybe one of the most important properties of transition metal dichalcogenides. And in particular, this spin splitting actually allows you to excite electrons in one valley or in the other valley if you are capable of coupling the spatial degrees of freedom to the spin, for example. So if you shine circularly polarized light to these dichalcogenides, we are capable of exciting electrons in one valley or in the other valley, which is, of course, something extremely important for valleytronic applications in two-dimensional materials. So in dichalcogenides, one can actually create valley currents with light, for example. And this is all thanks to this spin splitting that comes from spin orbit coupling, from the Ising spin orbit coupling. All right, good. So now let us see how we can use this spin orbit coupling in proximity effects, or what is the impact of this spin orbit coupling in proximity effects. So what we are going to do is we are going to consider a very, very simple heterostructure. So we are going to take one of the ferromagnets that we were discussing before. So in particular, let us take just chromium bromide, for example, that it's a two-dimensional material that has out-of-plane magnetization. And let's put one of these 2D dichalcogenides on top of chromium tribromide. So what actually happens is that the magnetization of this chromium tribromide modifies the electronic structure of the tungsten diselenide, just coming from the, let's say, van der Waals forces that you have, from the van der Waals coupling that you have. And in particular, what you get is that there's a spin splitting in one valley with respect to the other that it's directly driven by the exchange coupling. So for example, if you start ramping up what is the exchange coupling between your two-dimensional magnet and the two-dimensional dichalcogenide, what you actually see is that you can essentially control the splitting of one valley with respect to the other valley. So what this actually tells you is that magnetization could, for example, control a valley current. So if you're in this situation, all your electrons will belong to one of the valleys, and therefore all your currents will be valley polarized. And now the interesting thing is that since we have spin orbit coupling, different types of magnetizations can have different types of effects, right? So let us now consider a different two-dimensional ferromagnet, so chromium trichlorine, which is a van der Waals ferromagnet, but now it has in-plane magnetization. So for this chromium trichlorine, essentially you don't get any splitting on your K and K prime bands. So no matter how strong your exchange coupling is, then K and K prime are always degenerate, and the only thing that happens is that you open up a gap here at high energies at the endpoint where they cross. So in other words, thanks to the Ising spin orbit coupling, you can distinguish if a two-dimensional magnet is an out-of-plane magnet or an in-plane magnet. If your magnet drives a valley current, then you have an out-of-plane magnet. If it doesn't, then you have an in-plane magnet, for example. And this is one of the very nice examples of how by combining different two-dimensional materials that by themselves, they are relatively, let's say, simple, like a semiconductor and a metal, you can get extremely interesting behavior, even from the applications point of view, for doing for example, Valley transistors,
How do you measure?
Valley currents. You could do it optically also. So you can excite your different say electrons to different valleys optically, and you could also measure it optically through absorption, for example. And you could also use, let's say, inverse Valley Hall effect, for example. So dichalcogenides also have Valley Hall effect, and with inverse Valley Hall effect, you can also measure Valley currents. It is, of course, not as easy as with spin currents, but it's still doable. Yeah, all right, great. So now I think that it's a very good time to make a second break. So for the break, again, you can go outside, get some air, but if you want to think about something, what I would like to ask you to think about is what are the different symmetries that each of these 4 two-dimensional materials break? And some of them we already briefly discussed, but just think about which terms of the mean field or which kind of effective models you would need to use to describe the electronic structure of these 4 two-dimensional materials. And again, as before, you can take a picture if you want, and so forth. So I would say that we can stop here for